Good evening, everyone. Thanks for coming. Um, so I think this is the last time we're going to meet about these math review sessions, unless you require to have another one in the future before you start, solving your homeworks or you want to clarify something. So what we have for tonight is the introduction to Laplace transform um, and how we are going to use that for solutions in petroleum industry, in reservoir engineering specifically. So the objectives of this lecture is that you are aware that you are familiar with the definition of the Laplace transform and its inverse. So the definition of Laplace transform is the integral from 0 to infinity of the exponential function multiplied by a certain function of time, or t in this case. The integral looks pretty, well, it doesn't look very difficult in a sense. For example, if you assume that ft is equal to 1 or ft is equal to t or whatever the other function, you will get the Laplace transform only by integration by parts, like until you get sick of integrating by parts repetitively. But the inverse Laplace transform is quite more complex because it involves the integration in a complex plane. This guy over here is in an imaginary number, right? So trying to do the inverse Laplace transform is like most of the times impossible. So Dr. Blasingame has a joke to start this, so I think I have to tell it on his behalf. Otherwise, you cannot say that you took 620. So he always says that the Laplace transform is like marriage, that it is easy to go in, but almost impossible to go back. So yeah, now you can say that you took classes with him. So this is the definition of Laplace transform, right? And Laplace transform is used, and we'll cover that later today. We basically use it to reduce a partial differential equation to an ordinary differential equation. So if we basically get rid of one derivative that it is in terms of time, and we reduce it to an ordinary differential equation that it is in terms of space, x, y, r, theta, whatever the coordinates are. So yeah, that's like an introduction about this topic. So you are going to be familiar with the unit step function, that it is basically an impulse, saying that the unit step function is going to be 0 in case that the t is lower than a, and it's going to be 1 if t is greater than a. Most of the times, and in engineering purposes, a it's a starting point, right? So it is equal to 0. So that would be like the application for our case, right? We are going to cover the Laplace transform numerically and the inverse Laplace transform numerically as well. These methods, the step data function, the piecewise linear data function, and piecewise log linear data function, are methods to apply a Laplace transform numerically. This is not very common in reservoir engineering because, well, what you want is to come back from Laplace transform, right? And to have actually equations to use for interpretation. But it can happen that you have a set of data in terms of t, and you want to apply the Laplace transform to that set of data, that you don't have necessarily a function defined, but it is only data. So these are the the methods that you should use. We're going to talk about how to apply this the Laplace transform to solve partial differential equations, and we're going to talk about some properties about the Laplace transform. All right. We're going to cover the some of the techniques for numerical Laplace transform and numerical inverse transform. Okay. Yeah. Well, I'm going to come back to this slide by the end of the class. Well, you'll see why. So first, as you may be related to the partial differential equations, such as heat equation or diffusion equation or diffusivity equation, in our case in petroleum engineering, you have partial differential equations that are functions of space and time. Space is defined as x, y, r, z, and the time is, well, is defined by the t, right? So you could, there are techniques that you can apply to solve those equations, like transformations and change of variables, etc. But it is more convenient to use Laplace transform in our case in petroleum engineering, because you can include some effects of the wellbore. You'll see that later in the course with Dr. Blasingame, but it's more convenient for us, even though that we know that that we know the solutions in real space, in real domain, it is always better to have them in Laplace domain. So here what are the properties of the Laplace transform? So Laplace transform is an integral, as you saw, as such. Like given that it is an integral of the product of two functions, you can say that the Laplace transform of the sum of two functions, it's equal to the sum of the Laplace transform of each one of these functions, right? And it also has a property of factorization of constants, right? If C1 and C2 are constants, well, they can be factorized. So this is multiplied to the Laplace transform of the function ft, f1 and f2t in these cases, right? So when you need to denote a function that it is expressed in the Laplace domain, you can use either S or U. Those are the two variable functions that you will see in literature. And also, if a function is defined in a Laplace domain, you should always put this little hat here, this bar, okay? This is in the case of the Laplace transform, and in the inverse Laplace transform, well, those properties are also applicable, right? So you can distribute the transformation and factorize the constants. So here it is shown an example if ft is a constant. So you'll see that if you substitute the constant in the equation, in the definition, well, you take out the constant and you only have this this integral. So you perform the integral, and which is minus e, the exponential function over s, and evaluating in the limits of from 0 to infinity, all this thing goes to 1, and then you deduce that the Laplace transform of any constant is that constant divided by the Laplace variable s. Okay? So another common example is when the function is equal to t. So you substitute t in the definition, and then, as I told you, you integrate by parts. In this case, I think it is only required two times of this integration by parts, and you end up, you can conclude that when the function in real domain is equal to t, so it is going to be expressed in the Laplace domain as 1 over s power 2, okay? So if you do it for the square of t, you do the similar approach, and you end up, you can see a pattern here that it is, well, in this case for t power 2 in real domain, in Laplace domain, it is expressed as 2 over s power 3. So you can establish a pattern here, right? It's pretty, you can, it's intuitive, right? So in general, you can say that whenever a function of any power, such as n, where's the pen? So you have for n is integer, in real domain. So if you express it in the Laplace domain, it's going to be the factorial of n over s power n plus 1. Okay? So if you remember, I think last class we were talking about gamma function. We know that gamma function of n plus 1 is equal to n factorial, right? So, and we also agreed that for the case that n is arbitrary or real, not an integer necessarily, so you can say that if f of t, this case we'll say v, in Laplace domain, this is going to be gamma, the function gamma of v plus 1 over s v plus 1. So this is the general case, right? I think there is a demonstration after this. Yeah, there you go, real exponent. So if you generalize this case when p is the exponent, so you substitute the function t power p, then you arrange the integral, and it is straightforward to see that this is the definition of gamma function. Right? And you end up with this. So in these cases, when you apply the Laplace transform, I recommend you to look at the restrictions of them, because sometimes the coefficients that you may need to use are not within the range of applicability of the transformations, but that's rare cases, but it's always good to keep that in mind. So one of the most important cases, and it is directly the application to um, the partial differential equations that you're going to deal with in this course, is when you deal with the time derivative. So the diffusivity equation for linear flow, you'll see, sorry, this is P. XD is equal dPdt, right? So this is you may know it as the heat equation, as the diffusion equation. In this case, is the diffusivity equation, right? For linear flow. So what you do here is to apply the definition of Laplace transform to get rid of this guy. Doing that, you can reduce this. Well, just remember that. I'll back to that. When you substitute some derivative of a function here, then you integrate by parts again, and then integrate and integrate and integrate, and you come up with this expression, right? So what it tells you is that in order to get the Laplace transform of a derivative, you need an initial condition, right? I'll try to show it more clearly here. So, sorry about that. Let's start over again. So if you apply the Laplace transform to this part, and you remember this formula over here, so you will see that is S times PD, which is function of XD. But here is already S, already in terms of S hat, right? Minus PD XD. If the initial condition turns out to be 0, well, this is reduced to SPXD 0. Yes, right? Okay. Just remember this part. This is going to be right hand side. Let's see if I don't lose that. Okay. And you can apply this whenever you have the second, third, the n derivative of mt. It is the same. It is a succession of sum. It is a sum, or yeah, in a sense, it is a sum of terms of fs times n power the number of the derivative here, right? And and you have to have as many conditions as you have derivatives, right? So here and here, it is in the case that, I don't know, you have, for example, n equal to, well, you have to have two conditions, right? And what happens when you want to apply for a derivative in terms of x? So you substitute this in the definition, and since this integral is in terms of dt, well, you can take the differentiation, or the differential out of the integral, and you end up with this. So in general, if you apply the Laplace transform in terms of t to a derivative in terms of x, you have the derivative of x of the Laplace transform of that function, right? And here it is the same. So if we go back to our example here, here it's squared. Sorry. So what happened if we apply the Laplace transform to the left-hand side? So we see our formula here. Right? Therefore, if we equalize these two, we get this. Right? Bar, yeah. Sorry, thank you. Good catch. Okay. Note that here I am using the notation of an ordinary differential equation, v, instead of the partial. Okay. So if you arrange this, right? And you already know by inspection from previous classes that the general solution is this, right? That's it. So this is the simplest case. You're going to be dealing with radial flow, which is basically the same, but you're going to change the coordinates a little bit and some transformation. It's kind of tedious, but okay. These are some properties of the Laplace transform. So if you have a function that it is multiplied by an exponential of some constant t, well, this is called the translation theorem, and the Laplace transform of a function of this shape is going to be this, the Laplace transform of this function, but it's going to be evaluated with in the kernel of s minus a. So there are so many properties here, like 3 or 4 examples. The scale change, if the function is multiplied, if every t is multiplied by a constant here, well, you only have to, oh, is this the one? No, here. So you divide the function and you substitute everywhere where S is supposed to be by S over S. Here is the derivative of the function with respect of S. I think I have used this a couple of times in my research, so well, you may need to focus on this later. But in this case, if you are going to get this derivative, so you have to remember the Leibniz rule. I think we covered this on our first meeting, right? Uh, the the derivation of this is kind of tedious, but everything is reduced to integrate by part. And in general, if you are going to take the n derivative of the function of s, um, well, no, this is in the other way around, right? So the Laplace transform of ft tn is going to be minus 1n, the n derivative of s over dsn, right? It's basically the same here. Okay. What other properties we have? Yeah. Here is the Laplace transform of an integral with respect of time. It, here relies. This is reduced to some manipulation of the kernel of the integral, but at the end of the day, you end up with this relationship, right? If you are going to take the Laplace transform of the integral of the function in real domain, this is the equivalent in Laplace domain. Okay, so in general, if you go to your Laplace transform tables that are available somewhere in the internet, here you'll find out many more of these properties and functions, and here we are only showing the basic ones, right? I have to tell you that these tables. This particular table is from 1966. I have another one that it is better. It has more transformations in a more direct form that are from 63, but still those are basically the same Laplace transform and inverse Laplace transform that exist in the literature. Not significant improvements have been made since then, and you can try to solve this to obtain the Laplace transformation or inverse Laplace transformations using Mathematica, but Mathematica will not get it because it has only the functions that are available in the literature. So yeah, basically whatever is in these tables, it's what there are. Okay. Yeah, and I think that's it about the direct transform. You can take a look later to this. Well, let's go back to the lecture. Finally, we got to the convolution theorem. The demonstration of this It's not trivial. It's not easy at all. So because you have the Laplace transform, of the integral Ct fu gtu minus u du is equal okay, so that's basically what it is saying. The importance of this relies on the Duhamel's principle. So when you're working with your solutions for radial liner or whatever kind of flow geometry of flow you're dealing with, you're going to see and you're going to be dealing with constant pressure. Oh, come on. Oh, come on. So you're going to be dealing with constant pressure and another with constant flow rate. The difference between these two is the inner boundary condition. Okay? So the link between these two is the convolution theorem, at least mathematically. You'll see it when you get there in the course. So this is why it is here and well, its application. Okay. So the next part is if you get a set of data of time and you know any kind of response that you're having, let's assume that this Ft is pressure, P of t, you have a set of data of time and a set of pressure data, right? And for some reason you need to take the Laplace transform to this set of data. So what you do is basically to assume that for each one of these points you have a straight line. And you set a set of functions based on the straight line equation, and then you apply the Laplace transform to this set, and well, for the different points of time. So you end up with this relationship, right? Honestly, I never seen this application like in reservoir engineering, but well, you may need it. You may need it for research, or you never know, right? Yeah, you continue here with the derivation, and you end up with the function expressed in Laplace space based on a set of data of t and ft. Well, we're going to call it pt. So you end up with this equation in the Laplace domain based on a set of data in real domain. Okay. Another method which is very similar to the previous one, you'll see it why, is the piecewise log linear data function. So if you have a set of data, again, DFT, right? And in here, note the scale, it is logarithmic scale here, and this is logarithmic scale here, right? So if you want to apply the method that we just talked about to this case where everything is expressed in a log-log scale, you have this expression, right, which is a power law. So if you take the log on both sides, you end up with P1 log t plus the log of I1, right? So in this case, you already have a straight line equation in terms of logarithms, right? But here it has the particularity that when you do the math, when you do the algebra and some calculus here, you end up with functions expressed in Laplace domain expressed in terms of incomplete gammas, right? The one we talked about last week. So when you have a set of data in a log scale, the log of t and the log of p, function of t, right? If you transform this to Laplace domain, you get this function, okay, in terms of incomplete gammas. So both methods have the same root, but they end up to be expressed in such a different manner just because they are in log-log. So it's a big deal. Okay, the numerical Laplace transform and an inversion. The class ends at 9, right? 9:10? Okay. Okay, I'll try to cover this, and I would like to introduce you to the safest algorithm. So, well, the first thing that appears in the notes is the numerical Laplace transform and inversion. So here, I think there are two methods that are in the notes for Laplace transform numerically, as in the other cases that you were applying Laplace transform to a set of data. I've rarely seen the real application of this. There may exist, but honestly, I've never seen it. So the first one is the Gauss-Laguerre formula for the numerical transform. And here, well, I don't think this one is covered later. I don't remember. And this one, the Gabor. So just to make clear, this one is from Laplace, from real domain to Laplace domain. And this one, which is the best friend of whoever do analytical analysis of reservoir modeling, is from Laplace to real domain. So if you remember, the definition, the analytical definition of this is from the integral from alpha minus infinite in the complex and whatever, right? something like this, some very, very ugly integral. When you are not able to do this, you do that. Okay? So that's basically what it is. I would like to cover this later because safest algorithm is the most important part, I guess, of in the numerical methods. So to apply the Laplace transform numerically, this is basically a numerical integration. So that's why I don't know if we talk about this in previous lectures, but one of the methods to integrate numerically is the Laguerre quadrature. So here, if you, based on the definition of the Laplace transform, if you arrange this such as it is expressed in this way, and then you define a certain function g of x, defined like this, so you can approximate the integration of this function by the summation of this function times this a weighted factor, right? So this is basically what it is happening here, right? Sorry. What we have here is an example. If you want to apply the numerical Laplace transformation to f of t equal t, so we already know from previously that the exact Laplace transformation is this one, right? We got this by integrating by parts. So if you apply the formula of the Laguerre quadrature, you end up with, would it be 1s summation of yi xi of s, right? Yeah, it is here. So if you assume an n equal 2, so you expand this summation if 1 of s, which is this one, but you also have it here, right? So you can put it already here. Of the weighted factor xy plus xy y1, right? 1, 1, 2, 2. Sorry about that. And you get these functions in from any handbook. In this case, it's Abramovitz. You get these values, and you end up that this sum is equal to 1. So this is reduced to this, to the analytical expression, right? So you can use as many terms as you need here. Here, this is a simple case that you only reach the solution for using 2 terms, but there may be cases that you need to use more. You can check that, checking the convergence of your solutions. Okay. So another method for Laplace transform. Well, this is for Laplace transform inversion, which is to express the Laplace transform as a polynomial, and then after a lot of mathematical manipulation, you set up a system of equations such as you determine the coefficients of the polynomial. Which one is this? So I want to cover the safest algorithm in a bit more detail because that's the most common tool that it is used in this in the industry or this part. So we already agreed that if you remember the solution we had, PD is equal to C1 E minus XD squared of X, and this is plus C2 E XD XS, right? This is the general solution. If we get a particular solution, let's say that C2 is 0 given boundary conditions and C1 is 1 over S. Let's say that. Then we have our particular solution given by this. Okay? In this case is pretty simple. You can find this in tables. This inversion exists. Oh, I lost it, but that solution exists. But let's say that it doesn't. So if it doesn't, you have to translate this to the real domain, some real domain by some using some technique. These techniques, or the most common I already told you, is safest. Safest, Gabor safest. And another one very common is Crump algorithm. We are going to focus only on this one. So the one that originally deduced this method was Gabor, right? He expressed it in this way, but turns out to be kind of difficult given this one, because for each term this guy changes the sign, so it becomes very difficult, and it is also expressed of a binomial coefficient or whatever that is. Oh yeah, right. Here it is. Right? But later, Stafest came and arranged this formula, this inversion formula, and expressed it as simple as this. Okay? It basically says that you are going to evaluate your function in the Laplace space with S being equal to the natural logarithm of 2 over t times this one. So this n over here, you may think that it is related to the accuracy, but it is not necessarily. So let's say that you want to use two terms. So this would be expand like this, v1 of the function t multiplied by 1 plus v2 of the function evaluated in this guy times 2, right? Where v1 and v2 are computed with this guy. So this one is the most difficult part in programming this. Difficult relatively, but you may find some some problems by, with it. Only it may require a couple of hours, but you'll get it. Um, it's pretty straightforward to do this using Excel, only the cells of Excel. You don't even need to use the Visual Basic inside Excel. You can just do that if you already know these V's, right? And somebody coefficients. Somebody, I'm not gonna say who, give this homework. And these V's are already computed here. So if you are going to use two terms, these are the coefficients. Four terms, these are the coefficients. Six terms, and so on. Somebody, I'm not gonna say who, already did that. So, well, you have it there. And unfortunately, you may be required to compute by yourself these V's, but at least you have a framework to compare your results. Okay, so this is more or less what we were talking before, that you may think that this, since it is a numerical method, you may think that as many terms as you use, you will get more efficiency, more accuracy, right? This plot over here show you that not necessarily. So if you use two terms, so this is the exact solution, right? And if you use two terms and four terms, six terms, and so on, the result approaches to the actual solution until n equal to 16. From here, if you exceed 16, you may start having numerical instability, or the algorithm becomes really, really unstable for large n's. So, but you cannot use low n's either. So this is the problem that safest algorithm and Gaber's safest algorithm may have, because you actually don't know what's the exact solution. So what you do is to try with two, try with four terms, try with six terms, and then when you reach a certain convergence, well, you may say that that is the solution. If you already if you have taken 629 with Dr. Balcon, he developed a code in Mathematica which is pretty accurate. Using Mathematica, the accuracy is basically, you may say that it is infinite, but it's still a numerical method. So, but it's the best approach I've seen. Seriously, it is based on Gaber, but it is not Gaber Stafes itself. So it is called just Gaber raw win. But the base is Gaber, so It is the same method, but expressed in different manner. Okay, so I think that's it. That's everything that I wanted to cover with you today. Thank you for coming. If you have any questions, well, happy to try to answer them. No. Anyways, if you have questions, you can send me an email and schedule an appointment. Come to the office, and well, we can work them out. Okay. Well, good night. Thanks for coming. I'll see you later.